Hi, this is Tim Tighe recording my After Café talk, How Rough is My Surface? By the end of this talk, you'll see that it's going to depend on the technique that we use to measure that surface roughness and the conditions under which we measure the surface roughness. Before we can talk about surface roughness, we have to define surface roughness. Surface metrology is the measurement of the small-scale features on surfaces. These small-scale features can be broken up into primary form, surface waviness, surface roughness. The waviness is considered the more widely spaced components or the lower frequency components of the surface texture. Surface roughness, often shortened as roughness, is the higher frequency component of the surface texture, or the smaller features that make up our surface texture. Inside the materials characterization lab, we have access to several techniques which are able to measure surface roughness. We have access to optical microscopy, which will do Z-stacking. We have access to stylus profilometry, which will do line profiles, and we have access to optical profilometry. We have two separate optical profilometry. The Tighe is a white light interferometer. The Quantification is a focus variation, laser scanning confocal, and a white light interferometer system. The Tighe is using a white light source centered at 580 nanometers. The Quantification is using a violet laser centered at 404 nanometer. White light interferometry is a technique that uses a special objective on the instrument. The objective has a beam splitter internally, and the white light source is split into two paths. Half the light reflects off of an internal reference, half the light reflects off of our sample. These reflected light paths are recombined at our detector and summed. The system is engineered so that the path lengths are the same, or zero optical path difference, when the sample side is at the focal plane of the objective. The center interference fringe then becomes our probe as we scan vertically for where each pixel came into focus based on a maximum voltage. Our image is then made up of this XYZ point cloud based on the pixel positions and the measured Z position. Laser scanning confocal uses a light source that is directed through an illumination pinhole. The laser light is reflected and scattered by the surface and directed through a confocal aperture and onto the photodetector. The second pinhole is acting as a light sectioning filter. The photodetector is registering a high signal value for the regions of the surface that are in focus and a low signal value for the regions of the surface that are out of focus. A vertical scan is performed while we raster the laser in an XY scan, building up a 3D measurement of the surface. It's very similar to the white light interferometry in that we are scanning vertically and we are measuring where maximum intensity happened. Instead of having this interference fringe set up at focus, instead we have a very sharp intensity peak at focus. The optical resolution of optical profilometry is going to depend on the numerical aperture of the objective that we are using. There are several various conventional resolution limits, and their definitions are here on this slide, but essentially the common formula is that our lateral resolution is going to be equal to a constant times the wavelength of light divided by the numerical aperture. Optical resolution is also going to be limited by the spatial sampling of the system. The spatial sampling is the field of view of the objective divided by the number of pixels present on the CCD camera. This will give us the dimensions of the camera pixel. Using a lower magnification objective, for example, the Tighe 2.75x has a 3 millimeter field of view. If we just simply do the calculation there, 3 millimeters divided by 1024, we're going to have a 2.9 micron pixel size. The 50x objective has a 175 micron field of view. Doing the math there again, we're going to end up with about 170 nanometer pixel size. So very different pixel sizes, just switching between objectives. Let's take an example of the effects of optical resolution and spatial sampling on our roughness. In this example here from the Zygo, this is the 10x and the 2.75x. You can see the optical resolution and spatial sampling for each objective in the image. SA represents our average roughness. XQ represents our surface RMS roughness. And if we look at this, we can see that the 2.75x optical resolution and spatial sampling is so large that essentially we are acting like a low-pass filter, and we're not getting any of the high-frequency data. We can see that in the cross-trace, and we can see that in the SQ, which basically is measuring about 112 nanometer RMS roughness. Now, for the 10x data, we have a much smaller optical resolution and spatial sampling as compared to the 2.75x. The cross-trace line there, you can see a lot more high-frequency data in there, and our SQ jumps all the way up to 476.2 nanometer roughness. So just by changing the objective, changes the numerical aperture, changes the fields of view, it actually changes both the optical resolution and the spatial sampling, and it changes our values. So again, this is where it starts going into that category of it depends on how we measure our data on what our actual surface roughness is being reported. Both of these are correct for those objectives. Taking this example forward again now to the 50x objective, we can see that keeping the optical resolution the same because we are keeping the same numerical aperture of the 50x, but changing the spatial sampling by changing the internal magnification on the Zygo, that also has a big effect on the RMS roughness or average roughness that we're reporting. So the 50x.5x has an RMS roughness of 657.8 nanometer roughness, and the 50x1x is up to 742.4 nanometer roughness. So depending on how we look at this surface, whether it be the 2.75x at 111 or the 10x at 476 or the 50x.5x at 657.8 or the 50x1x at 742, these are all correct. It's just under the conditions that we have measured it. And that's why it's so important to maintain consistency in your measurement conditions so that you have direct comparison of your data. Now, the difference between the Keonce and the Zygo will be the light sources that we're using and the numerical apertures on the objectives. They're very similar numbers. You'll be in the same ballpark for the same fields of view, but the fact that the Zygo has a 580 nanometer light source and the Keonce has a 404 nanometer light source, that's going to affect the optical resolution difference between the two systems, and they have different cameras. The Zygo has a 1024 by 1024, the Keonce is 1024 by 768. So essentially, these small differences will affect the numbers reported from instrument to instrument as well. So now let's talk about the difference between techniques. So atomic force microscopy, also known as scanning probe microscopy, is a technique which provides 3D information by raster scanning a very sharp probe across a surface and basically measuring that surface topography. Now these probes can be very, very, very small, down to 1 nanometer radius or curvature probe. So essentially our lateral resolution is much better than what we're getting with an optical based technique. So AFM's lateral resolution is going to depend on two things. It's going to depend on the pixel size, and it's going to depend on the probe that we choose. For the pixel size, that's going to be based on the scan size that we choose to collect, and then also the samples per line that we choose to collect it at. So essentially, we're going to raster scan lines, and we're going to collect pixels across those lines. So this is an example here where we have 20 micron by 10 micron at 4,992 samples per line, 2 micron by 1 micron at 512 samples per line. These actually have the same pixel size. However, we can see in there that the collection time was very, very different for these two scans. With AFM, we can collect much smaller scans as well. So, we're typically scanning 50 microns and under, but it's very common to collect 2 micron scans and 250 nanometer scans. And again, how we choose to collect the samples per line is going to change that pixel. So on the left, we've got a 2 micron scan at 1024, giving us a 1.9 nanometer pixel. On the right, we have a 250 nanometer scan at 2048 samples per line. That is a 1.2 angstrom pixel size. Now that's really a bit of overkill on this. With a 2 nanometer radius of curvature probe, it doesn't make too much sense to really drop that pixel size much below, 2 nanometers, 1 nanometer, based on what we're able to resolve with the probe itself. But that was for this example here, showing that on the left-hand side, we're going to have a lot more of the surface there represented, where on the right side, we're zoomed in. We're going to have a much lower roughness, but we've actually getting more detail off of the small features that are making up the majority of the 2 micron scan. There are hundreds of different types of AFM probes. We have super sharp tips, we have truncated tips, we have dull tips, and it really depends on the application that we're doing for AFM. Typically for topography, we want a nice sharp tip. Based on the line profiles that we see on the right, we probably want either a narrow pyramid, a wide pyramid, or a narrow parabola in order to measure our surface roughness as accurately as we can get in there. The truncated tip and the wide parabola, you can see they are gliding across, and we're not getting a lot of the high frequency data in there. They're not able to go down into the smaller features on that surface. Now, vertical resolution really doesn't matter too much as far as the probe, as long as you have a nice discrete step. If it is a small step in the middle of features, then you're going to need that sharper probe in order to be able to get down to the lowest part and up to the highest parts. Now, the AFM images, they are always a convolution of that geometry. That's important to understand with what you're collecting there. Different techniques are going to give us different results. In this example here, we've got a stylus profilometer on the left, we've got the laser scanning profilometer on the right, and essentially you can see they're recording very different RA values there. So this is an example of a surface that has been measured. This is a very smooth surface. Now, this surface actually has small nanoparticles all over it. Now, for the Keon system, because we are raster scanning this system, we end up with a lot of interference lines superimposed on here. And so the roughness here, even though it's saying 8 nanometers, it's not really 8 nanometer RMS roughness here, because the majority of this is actually the interference fringes that we're getting from this. The Zygo does not raster scan its source. So essentially it's collecting all of its data in a continuous vertical scan. So because of this, we don't have the interference fringes that are present in the Keons on a very, very mirror polished smooth sample. So here though, we can see the lateral resolution for our best objective on the Zygo, the 50X, is not good enough to even visualize the nanoparticles that are on this surface. Taking AFM images of the same sample does reveal there are in fact nanoparticles on this surface. This is a 20 micron scan. We can see small particles everywhere. We can see that there might be some variation in particle size and things like that. But at 20 microns, these tiny particles are even hard to see in this scan here. This scan was taken at 20 microns with 512 by 512 samples per line, and we're measuring an RMS roughness of 1.84. This is the same sample collected at 10 microns. All we did was zoom down from that 20 micron scan to a 10 micron scan. And when we zoom down, keeping the samples per line the same at 512 by 512, we actually now have a smaller pixel size. So essentially we're seeing even more data, smaller high frequency data. The particles are a little bit easier to see here, but because we have now decrease that pixel size, we're seeing our RMS roughness climb up. And that's actually the trend that I would expect as we're now introducing the ability to see more and more detail on the particles and their deviation from the sample surface. Zooming in again, we now have a 5-micron scan. We can see the particles very clearly here. It would be pretty easy to go in and do cross-trace lines and get particle heights and all that kind of stuff. And we can see that our RMS roughness has again climbed up now to 2.22. Zooming in further, we now have a 2-micron scan. Very easy and to see these particles are coming in very clear, and our RMS roughness has climbed again to 2.36. Zooming in again now to a 1-micron scan, it would be very easy, and this was probably the scan size I would use for going after these particle dimensions on here. And again, our RMS roughness keeps climbing up because essentially we're getting more and more detail of these particles, and the particles are taking, they account for more of the image, so we're weighting it in that direction. And this is now zooming in one further, so now we are in a 500 nanometer scan size at 512 by 512, so we have under a 1 nanometer pixel size here, and our RMS roughness is up to 2.58. Very easy to get particle dimensions here. So even in the technique itself, it's important to understand all of these changes. So optical profilometry was not a good example for this sample. The quants, the interference lines, the zygote's inability to see them, and then the AFM, we needed to control the scan size in order to really, dial in the right size to give us both, what we're after as far as the particle dimensions as well as, surface roughness. That was an example of just the measurement. But one of the things that we need to talk about as well is what do we do with our data after we have the measurement. So the raw data on the left side here, up in the top left, that is raw zygote data for the sample that we couldn't see the particles on. And you can see that the sample was actually slightly tilted on the stage, and so we have this tilt to the sample. So if I apply a plane fit, that flattens that sample out. So the 20 micron scan for the AFM is just below that on the left, and again, you can see that tilt to the sample. Now notice the SQ in that AFM data of the raw data. It's saying I've got 8.5 nanometer RMS roughness. The roughness is being dominated by the tilt of the sample. Applying a plane flatten to get rid of that lower frequency tilt is what now brings us down into a nice flat sample where we're recording that roughness at 1.84. Now, as we zoomed in, we have in the top left, that is the 1 micron AFM image after we've done a line flatten to it. And you can actually see all of this strange shading that's happening around these particles. That is a mathematical effect from doing a first order line fit to this data. So essentially, you want to make sure that when you are post-processing your data, you're not introducing effects which will change your reported value. So what was better done instead of a first order line fit was actually a first order line fit with a threshold value for excluding the particles and flattening just with respect to the surface. When we are taking roughness measurements over on parts that have some kind of a form other than a flat substrate, that needs to be taken into consideration as well. This curvature would be considered the waviness. Now, that might be important. If we collected enough of a field of view of this, we could actually determine what was the radius of this part and all that kind of stuff. So there are times, when we want to look at the waviness and not the roughness, and then there's other times when we want to look at the roughness and not the waviness. So in this example here, if I do a form remove of a cylinder, and basically that's an F operator, I'll get into that in further slides. Essentially, I'm now removing that form and now looking at the roughness superimposed on that cylinder-based shape. To break down post-processing of our data, we want to just review really quick here what we're talking about. So we have our different components to our sample here that make up the full surface texture. So essentially we have the low frequency waviness, we have the high frequency surface roughness, we have potentially lay directions and all of that kind of stuff. So we're going to take that and now we're going to talk about our surface processing. So we can take our primary profiles, if this is a line measurement, or our primary surface, if this is a 3D measurement, and we can break this up into the various components. We have our low frequency waviness components, and then we have our higher frequency roughness components, and we can filter these out as we need. When we are doing our post-processing of our data, we want to consider what we are interested in. We're going to take that primary surface and we have the ability to break it up into its various components. The lower frequency waviness, the higher frequency roughness, or maybe we're actually after a very specific feature of a very specific size. We could even filter narrowly and just accentuate and go after those particular details. So we have our waviness. If we're interested in our waviness, then essentially we would apply a low pass filter. A low pass filter is going to allow the low frequency data to pass through while filtering out all of that short wavelength data. If we have a high pass filter, essentially we're going to filter out all of that low frequency data, and it's going to allow all the high frequency data to pass through. If we were interested in a very specific feature, we would control both the low pass and the high pass, and we would end up with this band pass filter. So the older terms, high pass, low pass, these are slowly being changed with S filter and L filter. So S filter is going to attenuate short wavelengths. L filter is going to attenuate long wavelengths. Now, this L filter could also be done with an F operator. That was the form remove operator, like I did previously, or explained previously, with a cylinder or a plane or a sphere or something like that. So typically, when we do AFM data or optical profilometry data and we are working it up and we are writing a paper or something like that, we want to make sure that we are mentioning in that data analysis not just the objective, not just the numerical aperture of the objective, not just the camera pixel density, the light source, as well as what did we do. So did we do an SL? Did we do that band pass? Did we do a high frequency S filter with a form remove, an SF surface? So we want to let everybody know exactly what we've done to that surface that we're reporting that roughness on. So this brings me to the last part of the talk, and that is that I've said that how we collect our data and what technique we use, what conditions we use, how we post-process our data, these are all going to affect what the reported surface roughness of your sample is. Now again, it's all correct as long as you are not introducing features like the bad post-processing example that I gave. It's just correct for those conditions. Now, this is interesting part of the talk in that, roughness is not actually always the best way to tell the difference between surfaces. These profiles all have the same line profile surface roughness, average roughness. So RA is not telling us anything about the difference between these 6 lines here that are present here. There are a lot of standardized surface texture parameters out there that can be used to differentiate surface topography beyond average roughness, RMS roughness. And a lot of times these give a lot more insight into the difference between surfaces than just roughness. Yes, roughness is great if, say, I'm polishing a sample for nano indentation and I have to have a certain RMS roughness. But if I'm trying to tell the difference between 2 surfaces, as we saw with those lines, it's not always the best way to do it. So I'm going to give an example here. So this is an example of 2 different common stainless steel finishes. We've got a 32 blanched versus a 32 ground. These are purposely designed to give about the same average roughness. It's a very different surface texture though. And you can see here, if I was going by average roughness, 1.55 versus 1.53, if I took a bunch of different scans here, essentially these are too close together for this to really, tell me any difference between these samples. However, by eye, there's clearly a difference between the 32BL versus the 32G sample. Now, I measured this on the Keonce, and one of the nice things about the Keonce software is if I collect several scans on one sample and several scans on another sample, I can let the software look at those differences. So basically what it does is it averages the images and it looks what's the differentiation between these parameters in the sample set itself, and then actually compare the two different sample sets, and then use that as a comparison for what are the best parameters to define the differences between these samples. Now, I know that this is very, very, very hard to see. However, if you just use your eyes and go down the middle, you can see that up at the top here, these are the recommended parameters. You can see how far away blue and red are the peaks are represented. Whereas basically, by the time we get down to right about in a third of the way down, those peaks become red and blue become too close together that those are no longer recommended parameters. So I'm going to zoom in on the bottom first, what are the bad parameters, and then we'll zoom in on what the top parameters are for this particular sample set. So the worst parameters are actually average roughness, RQ, and right above SA in this list was SQ as well, and things like that. So essentially, average roughness, RMS roughness tells us nothing as far as differentiating these two samples. Now, what is telling us a difference? Well, the 3-star or the highest recommended terms are the SDQ, which is the root mean square gradient, SPC, which is the average peak curvature, sort of like the sharpness of peaks. We have the SDR, which is the developed interfacial area ratio. We have the skew, which is the kurtosis of the sample. We have the density of peaks. We have the peak volume, material volume. We've got SSK, which is the skewness of the sample. We have the reduced peak height. So let's go into some of those terms and see if we can figure out really what this is saying for us. SDQ represents the root mean square of the slope, DZ, right? So this is basically telling us what is the steepness of the surface. SDR is indicating the rate of growth in a 2D area. So essentially a perfectly flat sample, the SDQ, SDR, these would be 0, right? If we get our SDQ to 1, it means we have this perfectly steep surface with no flat whatsoever. SDR, that would actually now start giving us what is the ratio of the increased area in there. Now, SPC, this is the peak curvature. And so basically it's, it's how sharp or how rounded we are. We have SPD, which is the density of peaks. We have SKU, also known as kurtosis. This is going to indicate the presence of inordinately high peaks and deep valleys or lack thereof. We have SSK, which is skewness. This is going to tell us how our symmetry is related to the mean plane. If we are favoring above the mean plane or below the mean plane or at the mean plane, we're going to get that with the skewness. We have SPK and VMP, which are going to give us the height of the peaks around the core surface and deep high peaks and low valleys. So taking that all into consideration and the fact that average roughness, RMS roughness is not helping us out here, we can see that if we look at those parameters, the SDQ, the SDR, the SPC, for the 32G sample, we can see that the SDQ is telling us we have steeper features. The SDR is telling us that we have a more increased surface area. The SPC is telling us we have more pointed peaks. The SPD is telling us we have a higher peak density. The kurtosis skewness is telling us that we have sharper peaks. The SSK, or skewness, is telling us that we have more data below the mean plane. And the SPK VMP is telling us that we have more peaks and volume at the extreme heights and valleys. So this is a good example, showing how, by eye, we're looking at these samples. We know there's something different between them, and roughness was not a good example for describing the differences between these samples. So this concludes my talk on what is the surface roughness of my sample, and I hope that I've shown that it really does depend on exactly how you've measured it, what technique, and the conditions that you've run that technique at, and that it's not always the important question. Roughness sometimes is just not useful in describing the difference between, the samples that you are considering, and alternative texture parameters exist for a reason. Thank you.